In this video, we're going to look at a concept called derangements. So suppose that I want to list the numbers from 1 to n such that the number k is not in the kth position for any value k. How many ways can I do so? This is an example of a general idea called a derangement. And a permutation, or bijection, is called a derangement if no element, I should rewrite that, if no element returns to its original position. So let's go ahead and just get our feet wet with a few examples. How many derangements are there of the sequence 1? Well, none, because if you permute the numbers from 1 to 1, the only place 1 can go is right where it started. So there are none. There's 0. We'll call this number D0 to represent that the number of derangements of, that should not be D0, that should be D1. We'll use that to represent the number of derangements on n objects. So, what about 1, 2? Well, the good news is I can do it. 1 has to go where 2 went, because that's the only other place it can go. And then that leaves 2 to just go where 1 was. So, there's going to be one of those, and we see that D2 equals 1. It's going to start getting a little trickier for 3 elements. So let's think about what could happen. Could I switch 1 and 2? Could they swap places? Well, I can't do that because if I switch 1 and 2, then 3 has to stay where it is, and as we said, we don't want anything to stay in its original position. So I can't just exchange 1 and 2. So let's say I send 1 to where 2 was. That means that 2 now has to go to where 3 was. Oops. And that only leaves 3 to go where 1 was. So that's that's going to be a derangement. But I could also kind of do the other thing. I could send 1 to where 3 was. But since I can't just swap 1 and 3, that means that 3 has to go in the second place, and then 2 has to go in the first place. And those are the only places that 1 can go. It can only go to the second place or the third place. And as soon as I sent it there, it was automatically determined what the rest of the derangement would look like. So that means that the number of derangements on 3 elements is going to be 3. For 4, it gets a lot harder, and we're going to break it into 2 cases. So we're going to break it into the cases of, does 1 swap with something? Does it swap with something? If the answer is yes, then we'll break it up into one case, and if the answer is no, then we'll break it up to another case. So if the answer is yes, it could swap with 2. And if we do that, then the derangements that I'll have will have to be, they'll have to start with 2, 1. And then I need a derangement of the numbers 3, 4. Similarly, if it swaps with 3, then I'm going to have 3 blank, 1 blank. And then this can't be a 2, and this can't be a 4. So now these are essentially going to form a derangement of 2 and 4, because, as I said, this is not 2, this is not 4. Lastly, if 1 swaps places with 4, I'm slowly running out of room here, then my sequence will look like 4, something, something, 1. In this case, this is not 2, This is not 3. And this is going to be a derangement of 3 and 4. So we see that we're already getting a kind of recursive relationship over here. So what I did is I picked which element that one was going to swap with. That ended up being, so pick what one swaps with. There are n-1 ways to do that. And then I'm going to find a derangement of the remaining things. So I multiply by the number of derangements on n-2 objects. Okay. So we can go ahead and do that in the specific example we're looking at. We're looking at n equals 4, so this is just 3 times the derangements on 2 things. There's one derangement on 2 things. So there are 3 ways to form a derangement where one swaps places with something else. So what if one doesn't swap places with something else? Well, if 1 goes to 4, well, that's a weird place to start. How about we start with if 1 goes to 2? Then my sequence will look like something, 1, something, something. And what we know is that this first blank can't be 2. It can't be 2 because otherwise 1 swapped with 2, and we already handled that case. So this one is not 2. This blank, since it has to be a derangement, has to be not 3, and this blank, since it's a derangement, has to be not 4. So what we see is that I now need a derangement of 2, 3, 4, which feels a little weird because 2 didn't actually start here. But still, what I'm looking for is I'm essentially looking for a way to assign us 2, 3, and 4 to different spots in these 3 things, such that 2 doesn't end up in the first thing, 3 doesn't end up in the second thing, and 4 doesn't end up in the third thing. And that's exactly what a derangement is, or that's what a derangement of 2, 3, 4 will accomplish, is it will assign 2 and 3 and 4 to those spots such that 2 doesn't end up in the first, 3 doesn't end up in the second, and 4 doesn't end up in the third. So that's one case. If I send 1 to 3, then what does it look like? I'll have something, something, I'll have 1 here, and then I'll have something else. And we see that we get, well, this first blank can't be 3, because then that would mean that 1 and 3 swapped places, and we already did that case. This can't be 2, and this can't be 4. So what I need to do for those is I need to find a derangement of 3, 2, 4 in this case, in order to assign numbers to those 3 spots. And last but not least, if we send 1 to 4, we get a similar picture where we'll have blank, 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 1, where this is not 4, this is not 2, and this is not 3. And I need a derangement of 3, 2, and 4. Or sorry, 4, 2, and 3 in this case. So what did we have? In this case, what I did is I pick what 1 goes to. There are n-1 ways to do that again. And I multiply by finding a derangement of n-1 things. Those things are kind of in a weird order, but you know, I can still do it. And there are, of course, going to be dn minus 1 of those. So what is this going to end up being? In our specific case, n is 4, so this is going to be 3 times d of 2, which is going to be 3 times, I didn't actually say what it was up here, it was 2. 3 times 2, which is 6. So this should be 3 times d of 1, nope, of 2, I lied. 3 times d of 2 plus 3 times d of 3, which is 3 plus 6, which is 9. So there should be 9 derangements, and we can probably write down what they are. They're going to be, so I'll write derangements of 1, 2, 3, 4. Well, we're going to have the ones where we have just nice swaps, so that's going to be 2, 1, and then I'm forced to make the last 2, 4, 3. I'll have 3, 4, 1, 2. That's the one where 3 and 1 swap. And then we'll have 4, 3, 2, 1. That's the one where 4 and 1 swap. So those are all the swap ones. And then we're going to have the others where there's not a swap. So this might be a little tricky. So I'm going to need a derangement of 2, 3, and 4 to go here. So the derangements are going to be 3, 4, 2, and then 1. Or I could do 4, 2, 3. Basically, I just thought of taking this and then shifting it 1 to the right and 1 to the left, looping kind of around. That's how I did those in my head. So those are some ones where 1 ends up in the second slot, and then I could have, let's try to be consistent in how I'm doing this. I could have 2, 4, 3, and then 1 here, or I could have 4, 3, 2, and then 1 here, or I could have 2, 3, 4, 1, or I could have going to be 3, 4, 2, 1. And those are my 9 derangements of the numbers 1 to 4. And in this, we kind of came up with a nice general formula. The number of derangements ended up being n minus 1 times both dn minus 2 plus dn minus 1. Now, we're actually going to end up coming up with a general formula, a explicit formula for derangements, which will look something like the sum, and this is going to look a little weird, from k equals 0 to n of negative 1 to the k times n factorial over k factorial. This isn't exactly how it's written in the book, but I promise you it says the same thing. This formula can be derived using this recurrence relation, but if you want to do so, you're going to have to go through another recurrence relation. Or you can do it using the inclusion-exclusion principle, and that way doesn't use any recursion or recursive relationships or induction or anything. You just directly do it using inclusion-exclusion. So that is kind of the idea. So we're going to talk about how you can derive this formula in those 2 different ways in the next video.